Okay, very good afternoon to all of you. I am Shailendra. I am Assistant Manager for LCMS department from Shimarju. Today I am going to discuss about the basic principle of the LCMS and LCMS system. First of all, what we will do, we will try to understand what is the triple quadrupole, what is the LCMS, what is the basic function of the LCMS, how it works exactly, and after this we can exactly see how we can inject the sample, how we can get the data, and how this type of the instrument is helpful for the targeted proteomics experiment. What is a mass spectrometer? A mass spectrometer is an instrument that measures the masses of the individual molecule that have been converted to ions. A mass spectrometer is a universal ion detector. That means what is the basic requirement for the mass spectrometer? You should convert the compound into ionic form. A mass spectrometer is not a universal detector, it is universal ion detector. Therefore, you have to make a condition feasible for the ionization of your compound. It does not mean that you can analyze each and every compounds which are present in the sample. You have to make sure all these compound, at least the targeted compound should ionize, okay, and this ionized compound you can separate based on mass to charge ratio, and you can do the analysis, qualitative as well as quantitative analysis. How to ionize your compound, how to separate this compound, that we are going to discuss later. But basically what is a mass spectrometer? Mass spectrometer universal ion detector. LC gives one dimension information. To feed the sample on the mass spectrometer, either we can use a LC as a front end, or we can directly insert the sample into the system. Based on the property of compound, we can select any type of detector. You can only get the information about the time and the intensity. That means if you want to identify a compound under same condition, you have to run a standard, you have to match a retention time. Retention time is the time from the injection of the sample to get a peak maxima. The time is known as retention time. By matching the retention time of the compound under identical condition, you can identify a compound, and based on the response or intensity of this compound, you can quantitate your compound. Okay? But there is a possibility that, for example, if you are trying to do the sample analysis from the complex matrix, single peak doesn't make only one compound. There is a possibility 2 or 3 compound may correlate, but you cannot distinguish by only LC, right? In that case, you can use a MS as one of the detector. MS, what is the information you are getting? Not only the retention time, but based on the mass spectra. Mass spectra like mass to charge ratio, you can do the confirmation. There is also possibility 2 or more compounds which are eluted at the same retention time may have same molecular weight. Okay? How you can confirm the peak or compound which is eluted at this retention time is pure or not, right? For example, you are doing the analysis of the small molecule from the matrix like plasma. The molecular weight of your compound is 490. Okay? You are getting the particular retention time, for example 2 minutes. You are getting the M by ratio 491 or 489. Okay, 491 in positive and 489 in negative, based on the protonation and deprotonation. Okay? But there is a possibility when you deal with the analysis of such compound from the matrix, few of the compound, for example proteins or carbohydrates or any other biological compound may have the same molecular weight. It can elute at the same retention time. How we can confirm it is only single compound or multiple compound? In that case, you should add one more dimension, that is the LCMS. In LCMS, what are the information you are getting? The retention time from the LC, the molecular weight from the first MS, and fragmentation pattern from MS. Let us take the same example. The molecular weight of your compound is 490, and the interfering molecule also having the molecular weight of 490. You are getting a M by ratio of 491. But when you do the fragmentation, the product ion which forms for the compound of interest and the interfering molecule will be different. Okay? Therefore, what you have to do, you have to focus that product ion that is specific for your compound of interest. In that case, you can avoid the detection of interfering molecule, and you can quantitate your compound in presence of different biological matrix or interfering molecules. You can also do the LCMS MS analysis by using the IT TOF, ion trap with the time of flight. This type of the analysis may help for the structural elucidation of your compound, where we can get the accurate mass up to the 4 decimal. You can do the structural elucidation and formula prediction. The interface are present between HPLC and MS. HPLC, you are using aqueous or organic solvent with buffer. In HPLC, you have to use the volatile buffer. Why? Because if you are using the non-volatile buffer, in case when you are using in the MS, what happen? It get precipitated, it form the salt formation and MS get contaminated. Therefore, in the case of the MS, when you deals with the analysis, for the HPLC, you have to use volatile buffer or volatile organic solvent. The MS, you have to use a high vacuum environment and analyze based on mass user ratio. What are the different ionization terminologies are there? API is the atmospheric pressure ionization. Under API, there are two techniques. One is a ESI and APCI. ESI is the electrospray ionization technique. APCI is the atmospheric pressure chemical ionization. The one more technique is there, that is known as the APPI, that is atmospheric pressure photoionization. Different technique has different application. Based on polarity of your compound, you can select any one of the technique for the ionization of your compound. Let us see. ESI, that is the electrospray ionization technique. In this case, there are two concentrated capillaries that are there. From the middle capillary, there is a flow of the liquid or mobile phase coming from the HPLC. From the outer capillary, there is a flow of the nebulizing gas. Here we are using the nitrogen as a nebulizing gas. At the tip of the capillary, we are giving high voltage between 3 to 5 kilovolt. What happened? Because of the nebulizing gas, it nebulized into the fine droplet, and because of the high voltage, it formed the charge, either positive or negative, but it formed the single type of the charges. Then what happened? Due to the high temperature, the solvent start evaporating. There are two forces which are acting on the solvent droplet. The one is the Coulombic force of repulsion between same charges. The second is a surface tension. The surface tension try to put all the ions together, but the Coulombic force of the repulsion, they try to far from each other. And once the Coulombic force of repulsion overcome the surface tension, that is known as Rayleigh limit, then what happens? The ions get separated. Okay, it comes out, and finally it enters into the mass spectrometer to the desolvation line. Okay, this is a phenomena which occurs in the electrospray ionization. Generally, electrospray ionization used for the polar type of the compounds, and for the protein analysis, most of the cases, this is the only technique which are used for the ionization, ESI technique. Okay, this is the process which I already explained, how compound get ionized and enters into the mass spectrometer. The factor influencing the ESI ionization efficiency are mentioned here. Here we are using the LC fluid, the nebulizing gas, is polarized into the high voltage, it form the molecular weight plus 1, that is protonation or deprotonation. Protonation means addition of the H plus ion, deprotonation means removal of the H plus ion. Therefore, always you are getting, if the protonation occur, you are getting molecular weight plus 1. For example, molecular weight is 390, you are getting the spectra is 391. In case of the negative mode, you are getting 389. Okay, that is due to the protonation and deprotonation of your molecule. Then drying gas, that is used for the evaporation of the solvent. Because of that, what will happen? The droplet size will reduce, and then when the Coulombic, there is a competition between the Coulombic force of the exclusion and surface tension, and then there is formation of free ions, and that enters into the mass spectrometer. The next technique is the APCI. The APCI is the atmospheric pressure chemical ionization technique. ESI used for the polar compound, APCI used for the mid-polar compounds. How it works? Here also there are two concentrated capillaries are there, okay, and there is a heater plates are there. What happened? Here also we are using nebulizing gas. It nebulizes between this heater plate that is maintained at the high temperature, okay, and what happened? It formed the small droplet. Okay, the compounds are not yet ionized. There is a coronal discharge needles is there, that is maintained at the 3 to 5 kilovolt. When the compounds in the vapor form, they strike to this coronal discharge model. This is where the ionization takes place, nitrogen get ionized, and when it strike to your molecules, what happens that the charge get transferred and compound get ionized. This is the process of the chemical ionization. Okay. And then finally, the compound which are ionized get enters into the vacuum in the mass spectrometer. Generally, this type of the technique is used for the analysis of the mid-polar compound or compounds which are very difficult to ionize. The main difference in the ESI, the compound ionization takes place in liquid form, and in case of the APSI, the compound get ionized in the gaseous form. Okay. For example, steroids or vitamin D2, D3, this type of the compounds, we can use this type of the technique for the ionization. Then APPI, atmospheric pressure photoionization technique. In this case, the technique is almost same, but instead of the corona discharge needle, you are using the UV lamp at the particular frequency for the ionization of your compound. Okay. It generates the molecular ions in the presence of the air and the common LCMS solvent. They reduce the fragmentation by limiting the energy deposited into the molecule being ionized. Generally, this type of the technique used for the ionization of non-polar compounds. This is the process how the compound get ionized and the charge get transferred to molecules. I am not going to discuss in detail. Okay. The ionization potential, these are the different type of the compounds which can ionize or we can analyze by APPI, and these are different type of the potential which you can apply to that the laser beam so that the compound get ionized. Okay. Okay, this chart will help you based on the molecular size and the different polarity which technique is suitable. ESI you can use for the very polar to mid polar compound which having the high molecular weight compound also you can utilize. APCI used for the mid polar to non polar, APPI also similar way, and EI which is used in the GCMS is specifically used for the small molecule non polar compounds. The single quadrupole, this is the basic configuration of the single quadrupole that we are going to discuss. In any LCMS system, what it contain? It contains the interface, it contains the ion guides, and then mass analyzer and detectors. Okay. The interface, as I told you, are used for the ionization of your compound and to remove the solvent. The ion guides, here the ion guides are Q array and octapoles which are focus the ion in the same direction, and then mass analyzer, the different type of the mass analyzer you can utilize for the separation of the ions based on mass to charge ratio. Here we are using the quadrupole as a mass analyzer. Okay. How it work? It contains the 4 rods, the opposite rods having the similar type of the charges. We are providing the DC and RF voltage. The RF voltage are used for the acceleration of the ions in the forward direction, and DC voltage are used for the selection of the ions. What happens generally when a compound get ionized and then it enters into, this is the desolvation line where compound get enters into the mass spectrometer. All these things which are in the under vacuum condition, we are giving the primary, secondary and tertiary type of the vacuum. Generally for the low vacuum we are using the rotary pump, and for the high vacuum we are using turbomolecular pump which can use the vacuum up to 10⁻⁴ Pascal. Then ions enters into the ion guides. The ion guides, what is the main function? To focus the ions, okay, in the same direction. It avoid the loss of the ions. If the ion get lost in this, what happen? The total intensity will decrease or sensitivity will decrease. Therefore, in most of the vendor they are focusing for the development of this ion guides. So the more and more ion get focused, there is no loss of the ions. Okay. And for the ion guides we are providing the RF frequency. Why RF frequency? Because as I told you, the RF frequency helps for the focusing of the ions. Then it goes to the quadrupole. Quadrupole, along with the RF frequency, we are also giving the DC voltage. The DC voltage are used for the selection of the particular ions. The RF voltage for the movement of the ions in the forward direction. For example, if you want to analyze the particular ions, okay, of particular ion-Bison ratio, the instrument is tuned in such a way that based on the molecular weight, the DC to RF voltage is already tuned, because this LCMS or any LCMS, before doing the analysis you have to do the calibration of the LCMS. In the calibration you are using the different molecular size of the compound, okay, whose molecular weight is known to us and it is recorded by the software, and based on the molecular weight of that compound or that ions, it tune the DC to RF voltage, and the information gets stored into the instrument. When you do the analysis of your compound of interest, okay, for example, I want to do the analysis of the compound having the molecular of 390. The what happened for the 390, what is the DC to RF voltage is there, the information already stored, the quadrupole maintain that type of the voltage, only that ion get directed into the quadrupole or selected in the quadrupole, the rest of the ions get destabilized, it goes to the vacuum, and finally it goes to the detector. The detector is a electron multiplier with the conversion diodes, where ion strike is generate the electrons, and the electron get multiply and you are getting the results. Okay, you are getting the chromatograms. Just now we discussed about the basic model, that is a single quadrupole. Okay, what is the working of the single quadrupole? Now we are going to focus on the triple quadrupole, right? In triple quadrupole, how it works? It contains the 3 quadrupoles, Q1, Q2 and Q3. Batch filtration of the ions takes place in the Q1 and Q3. The second quadrupole only used for the fragmentation. Okay. How exactly it works? Here we can select a particular ion of interest in the first quadrupole. It passes to the second quadrupole. The second quadrupole, it contains some collision gas that is known as argon or nitrogen. Okay. And what happens? The ions are having some kinetic energy. You are providing some energy or some potential to your argon gas. It get vibrate. When it strike to your compound of interest, it get fragmented and it form the product ion in the Q2. This product ion gets escalated into the Q3. It gets separated and you are getting the more information. Therefore, to get the more information about your compound, you can use this type of technique. This not only the one technique is possible, there are different type of modes are possible, like the MRM multiple reaction monitoring, the precursor ion scan, the neutral loss scan. Okay, these are different type of the modes which are possible, and different modes having different type of the application. Okay, that we are going to discuss in subsequent slide. But what is in short, what is the difference between single quadrupole and triple quadrupole? Triple quadrupole, you can do the fragmentation of your compound of interest. You can generate more information, and by selecting the particular fragment ions, okay, you can do the quantification of your compound of interest. Okay. The quadrupole, we already discussed what is the principle of the quadrupole. It contains the 4 molybdenum rods, okay, and the opposite rods having the similar type of the charges, okay, and you are providing the RF and DC voltage, okay, but that is voltage is not constant, it get fluctuating. What happens when the ions get introduced into the quadrupole? Okay, for example, if the ions form the negative charge, okay, it attract toward the positive charge, but when it goes to that type of that quadrupole that rods, what happens? The charge gets changed to next rods, then ions moves to the next rods, and when it is going to reach to that rod, the charge again gets changed on the rods, it comes in. Like that way, there is a motion of the ions between these rods, okay, and then what happens? It moves due to the RF voltage, it moves on the forward direction, okay, and those ions which get destabilized, okay, it moves out, okay, and then it goes to the vacuum. Therefore, like that way, the ions are moving between these quadrupoles, and by providing the particular DC voltage, you are stabilizing the particular ambiguous ratio mass ions among this quadrupole, and rest of the ion get destabilized into the vacuum, and like that way you can select the particular compound of interest. What is the advantage? It is relatively inexpensive, reliable, there is simple to use, no high voltage are required, you are not applying any voltage here, mass scalar is linear, they limit a resolution up to 1000 to 2000, limited mass range up to 2000 AMU. Generally, the quadrupole you are getting a unit resolution. Okay, suppose there are 2 compounds having the molecular weight of 400 and 401.5 and 400.51, this compound cannot be distinguished, okay, because here it is a unit resolution mass spectrometer, okay, that means it can difference between 400 and 401. It cannot distinguish from 400.51 and 400.5, okay, because it don't have so much of the mass accuracy like time of flight, okay. The collision induced dissociation of the ion takes place in the collision cell, okay. Ion must be escalated with the sufficient kinetic energy and collide with the argon atom. Argon gas is called as a collision gas. As I already explained you, Once the ions get selected in the first quadrupole, it goes to the second quadrupole, where it collides with the organ gas of the particular an energy, and based on the collision energy, the compound get fragmented, and then this product ion gets scanned in the third quadrupole. Okay, this is one of the technique which are utilized by the Shimazu instrument, that is a ultra fast sweeper technique. What happened when you use the multiple type of the event? Okay, what happened, the ions coming from the first quadrupole, okay, it strike with the organ gas, it form the product ions. During that process, it lost some of the energy. Okay, the product ions which are formed in the Q2, okay, it lost some momentum, therefore it moves slowly towards the third quadrupole. If the next event will start, okay, it contains the similar type of the product ion, you may get the crosstalk effect. To avoid that, we have provided with this type of the technique, that is known as a UF sweeper. In the UF sweeper, there is this type of the alignment of the collision cell. What happen? It provides the pseudo potential. In pseudo potential, what will happen? Generally, when the ions get fragmented in the second quadrupole, okay, the ions are moves like this way. Okay, it moves slowly, it follows the longer pathway. But when you apply the pseudo potential, the ions swipe very easily from the second quadrupole. What will happen? You will not get the crosstalk effect. Okay, this type of the technique is very helpful to reduce the crosstalk effect when you deals with the multiple MRM events. Okay, this is a inside of the triple quadrupole. This is the interface. We can use the ESI or APCI. This is the DL, desolvation line. You can give the temperature for the desolvation line, so that it remove the solvent that is associated with the molecules. The ions get enters into Q array and the octopoles. These are act as ion guides that focus the ions in the same direction, and then these are the skimmer. The skimmers are used to maintain the vacuum difference. It enters into quadrupoles, where the selection of the ions takes place based on mass to charge ratio. Then this is a collision cell where the fragmentation will take place. The third quadrupole where the product ion gets scanned or detected, and there is a detector. Generally, as I said, there are three main interfaces are there: ESI, APCI and APPI. Okay, but most of the time we are using ESI and APCI. Okay, there one more also there, that is a deuce mode. Deuce mode means dual ionization interface. In that case, what happen? ESI and APCI you can do simultaneously. Okay, then the ESI technique is used for the ionization of the polar compound, APCI for the mid-polar non-polar compound. But suppose you have the mixture of the sample. Suppose you have the sample, it contains the mixture of the polar and non-polar compound. Okay, in that case, what you have to do? You have to first run on the ESI, you have to change the interface, you have to run on the APCI, and then you have to match the data. But when you have the deuce mode, in deuce mode we are using the ESI probe, but along with that we are using the corona discharge needle. What happen? Due to which you can analyze both the type of the polar and mid-polar compound by using this type of technique, and you can generate the data. These are some of the features of the instrument. Okay, I am just going to polarity switching. This is also one of the important function when you deals with the different types of the ions having different polarity. Okay, when the compound get ionized, some of the compound get ionized in the positive form, some of the ions get negative form. When you analyze the positive ions, all the voltage from the starting to end till detected get converted to negative, so that all the positive ion gets separated. Okay, when you want to ionize the negative compound, the voltage switch over from negative to positive. The switch over time is known as the polarity switching time. If the polarity switching time is very slow, what happen? During the switching time, most of the ion get lost, and because of that the quality of the data get reduced. Okay, therefore you require the polarity switching time should be very fast, so that you can analyze both the positive and negative time simultaneously, and you can detect the data. The scan, Q1 scan means you are scanning the first quadrupole, all the masses, second quadrupole and third quadrupole, it act as a ion guides. That means it is on the RF voltage. That means here the triple quadrupole works as a single quadrupole. Only you have to detect all the ions generated by the interface. Similar for the Q3. Then product ion scan. In the product ion scan, you have to select the particular precursor in the first quadrupole. It passes to the second quadrupole. It do the fragmentation. And what are the fragment you are getting? What are the products ions you are getting? You have to scan. This is you are getting the qualitative information. The two more scans are there: precursor ion scan and neutral loss scan. these two type of the scannings which are used for the screening purpose. When you want to screen the particular group of the compound, you can use this type of the scan. I am not going to discuss in detail. Most important is this one, that is a MSMS or that is a MRM. MRM is a multiple reaction monitoring. Okay. What you have to do here, the first quadrupole in the SIM mode, you are selecting the particular precursor ion, it passes to the second quadrupole, it gets fragmented, it forms the different product ion. Among all the product ion, you are selecting that product ion that is specific to your compound of interest, and the intensity also good. That means third quadrupole also in the SIM mode, and this from the precursor to product, that is known as the MRM transitions, and this is used for the quantitative analysis of the compound from the different matrix. Okay, this is the product ion scan. As I explained already, there are different type of the ions are formed. Only you are selecting the particular ions of interest. Okay, that goes to the second quadrupole. It gets fragmented, it forms the different type of the product ions, and you are scanning all the product ions. That gives the good information of your compound of interest, and this is very good qualitative tool. Then the precursor ion scan. Okay. In the precursor ion scan, what you are doing, your Q1 in the scan mode and Q3 in the SIM mode, that is the opposite to the product ion. You have to look for the group of the compound will have the common functional group or common precursor. For such type of the screening purpose, you are using the precursor ion scan. Generally what happens when the compound gets fragmented, it not always form the charged compound. Sometimes it may form the neutral compound and sometimes it may form the neutral plus charge. Suppose you want to monitor the group of the compound having the common neutral. How you can identify? You cannot monitor the neutral by any technique because it is not ionized, and this is a ion detector. So what you have to do? You have to monitor the difference. For example, the neutral molecule weight is around 100. Okay. The precursor molecular weight is around 500. Okay. If there is a neutral loss, you will get the product ion of the 400. Understand? 500 minus 100, that is the 400. That means if your compound giving the product ion of the 400, that means you can say that this gives the neutral of the 100. Okay, like that way you can identify how many compound in the sample gives the neutral loss of the 100, and that also one of the tool for the screening of the compound. Okay, this is very, very important, that you should understand what is the MRM. The MRM is a multiple reaction monitoring. It is a standard method for the quantification of the LCMS MS. Okay, how it acts as? In MRM you have to select the particular compound or ions of particular peptides of on the first quadrupole. It goes to the second quadrupole, it undergoes the fragmentation, and you have to select only that product ions, okay, that having the highest intensity. Okay. That means here the Q1 and Q3 both are in the SIM mode. Okay. Why the MRM is important? Because MRM has two outstanding advantages. It extremely good mass selective feature. Suppose you can take this example. There is a SIM analysis, single ion monitoring, and MRM. In single ion monitoring means you are only monitoring one ion of interest. Suppose your molecular weight of your compound is 500, okay, you are only monitoring the 500 only. But when you deals with the analysis from the complex matrix, the different molecules having the similar type of the molecular weight, and the baseline will not be stable, you are getting some unwanted peak. Okay. But suppose same molecule, if you try to monitor by MRM, in MRM what you are doing, the 500 molecule you are doing the fragmentation. Okay. Fragmentation you are getting the product ion of 200, 300 or 400. Okay. You are selecting the 300 as a product ion because it is giving the high intensity. Now the transition is the 500 gives the 300. Now what will happen? Because of this specific transition, you are getting the very good selectivity, you are getting very less noise, and signal noise ratio will improve. Therefore, the MRM is a good quantitative tool, okay, for the quantitation of your compound like peptides from the complex matrix. This is a comparison of the MRM and SIM. SIM only single line you are monitoring. In MRM, okay, you are monitoring the transition precursor to product.
So let us start from the HPLC first. So any HPLC which is connected to mass spec is called as front end system. Okay, front end HPLC. So there are different types of HPLCs available in the market, like conventional HPLC, fast HPLC, nano HPLC. Right now, what we are saying is, seeing here is UHPLC system. It's a fast HPLC system. UHPLC stands for Ultra High Performance Liquid Chromatography. Okay. So the name of this system is Nexera. Nexera stands for next era. Okay. So fine. First, I'll explain you the flow path of the HPLC system. So these are mobile phase reservoirs. Fine. Port A and port B is there. And okay, there are two types of configurations of HPLC available. One is called as high pressure binary gradient system, and one is called as low pressure quaternary gradient system. So high pressure binary gradient system means if you have two mobile phase ports, then there will be two pumping units, one for each of the mobile phase ports. So that will become high pressure binary, and binary why? Because there are two, so it becomes high pressure binary. Other model will be low pressure quaternary, where there will be only one mobile phase pump, one pumping unit and four reservoirs, and one pump is controlling all the four. Fine. Okay. So these two are pumping units. So from mobile phase here, it goes to first degasser unit. So from dissolved degasser unit, the mobile phase will come to respective pumping system. So suppose this is pump A. So pump A from degasser unit is coming to this. Okay. Now this pumping unit is dual plunger reciprocating type of a pump. So tell me what characteristic HPLC pumping unit should have. Sorry? Characteristics, speciality. What it should have? It should have
high pressure.
High pressure. No. I mean its pressure withstanding capacity should be high. Okay. So it should pressure withstanding capacity should be high. Second, it should give us wide range of flow rates, right? And then flow should be pulseless. So what do you mean by pulseless flow or pulseless output? Continuous output. Because from the column, your analytes will pass to the detector only when there is a flow, right? If that flow stops, then analyte will be stagnant on the column. It will not go ahead. So you want your analyte to continuously pass to the detector. So your output should be pulseless output. Now here you see these are dual plunger reciprocating kind of a pump. See, this is the plunger unit, okay, where mobile phase will get stored. These two are check valves. These two are non-returnable check valves. That means when this valve is open, this will be closed, and when this is open, this will be closed. This ensures that flow of the mobile phase will be unidirectional. Okay, if both the ends are open at same time, half of the flow might go this way and half of the flow might go this way. We don't want this scenario. So initially what will happen, this valve will open, mobile phase will get fill in this valve, okay, then this will get closed. Now the plunger will move and it will pass mobile phase to the column, and that time this valve is open. Now after the mobile phase in this particular plunger unit is over, it has to do refilling action, right? So that will take hardly milliseconds because the capacity of this plunger is 10 microliter. So this will take hardly milliseconds, but then for that millisecond also there is no flow on the column, and we don't want this scenario to happen. So instead of using only one reciprocating plunger, we use two plungers. So when this is passing mobile phase to the column, this will get refilled with the mobile phase and vice versa. Okay. So and back pressure withstanding capacity of this particular model is 19,000 psi. Okay, 130 megapascal. So you can use higher flow rates as well. You can use smaller particle size column, smaller ID columns, which normally tend to generate higher back pressure, but still those can be used on this particular system. Okay. After the okay, this is clear. After pumping unit, okay, I need to mix A and B, right, in one particular combination. So there comes a mixer. So here, whatever mixer we are using, yeah, just so this is the mixer unit. It is having microreactor technology. So okay, generally I told you this is a fast HPLC system. So fast HPLC system main use is reduction in the analysis time. So if my analysis time is only 5 minutes or 10 minutes, and in that I want to do gradient analysis, that means my A to B concentration is continuously changing, my mixer should be so efficient that within that smaller amount of time it should give me proper mixing. So this mixer is specifically designed with microreactor technology. So its mixing efficiency and mixing accuracy from run to run is very good. Okay. There are different types of mixer available: 20 microliter, 40 microliter, 180 microliter. So depending upon your requirement, you can select which mixer is good for your analysis. Of course, higher the volume, better will be the mixing, but increase in the system volume. So your peaks will come slightly late. So you will have to strike balance whether I want to finish my analysis very fast, or I want better mixing. So depending upon that, you will be selecting your mixer. So after mixer, your flow will go to auto sampler. This is the auto sampler unit. Okay, any auto sampler unit, if you see, it has 3 parts. Okay, one is high pressure valve, one is low pressure valve, and one is measuring pump or metering pump. So what is the function of measuring pump? Whenever you give command that okay, inject 10 microliter of sample, that is done by this measuring pump. Okay, so it will inject 10 microliter, 5 microliter depending upon the command. Now high pressure valve, your mobile phase will always pass through high pressure valve, and there will be sample loop attached also to high pressure valve. So whenever you do injection, mobile phase will switch, and it will flow from the sample loop, it will collect the sample, and then it will pass on to the column. So mobile phase is always passing through this high pressure valve. Now what is the function of low pressure valve? Suppose you have manual injector, okay, when you inject 2 different samples, in between the samples you perform rinsing of the needle or rinsing of the syringe, so that there will not be cross contamination, right? So when you are using auto sampler, that function also needs to be done automatically, and that is the purpose of this low pressure valve. So in between the analysis, whatever rinsing and everything happens, that happens because of low pressure valve. Okay. Now what is the feature of this auto sampler is it gives you very low carryover. What is carryover? It is almost near zero carryover. So what do you mean by carryover? Right. So you have to understand how injection happens. So there is a needle, right? You will put your samples in this auto sampler vials like this. Okay, you will fill in the vial, and needle will come and pierce through this vial and take the sample. So outer surface of the needle is coming in contact with the sample. Now if the sample needle goes there to inject a port and injects the sample, there is a possibility that whatever is stuck to its outer surface will get deposited on the injector port, and when you perform next analysis, even if you are not injecting sample, if you are injecting only organic solvent or only water, the traces of those residues will pass and give you response. That is called as carryover. Now in case of this auto sampler, this carryover is avoided by certain means. Firstly, this needle is coated with special type of material, polymeric material, which does not allow anything to get absorbed on its surface. Okay, so that is the one way you are not allowing carryover to occur. Okay. Secondly, there is another port which is given for rinsing. So there is an option of rinsing your needle's outer surface, okay, when it performs the injection. So injector port, so there are multiple options. One option is called as before and after aspiration. What does it mean is, injector, when you give command of injection, injector port will go to rinsing port, its outer surface will get clean, then it will come to vial, it will aspirate the sample, it will again go to rinsing port, its outer surface will get clean, then it will come to injector port and inject the sample. So this is the way how you can reduce the carryover. Thirdly, when carryover can come, when there is a contact between your needle and the injector port. But if I reduce this contact area, then there is a less chance of sample getting deposited on the injector port. So in this particular auto sampler, the injector port and design of injector port and needle is such a way that there is minimum contact area between these two, and that also does not allow carryover to take place. Fine. Also, this is a fast auto sampler. It takes only 10 seconds to inject 10 microliter of sample. So this particular function is very important when you perform fast HPLC kind of analysis. Because suppose this is generally for small molecule assay or something, if you want to quantify only one particular compound for your sample, okay, and your runtime is as short as 1 minute or 2 minutes. And if your auto sampler is taking 45 seconds to inject one sample, you are definitely losing on the throughput. In that case, you have to have auto sampler which can efficiently and fastly inject the sample, right? So that is why this can be coupled to the fast HPLC. This is a fast HPLC auto sampler. Okay. Up to this part is clear. Fine. We will go to the column. This is a column oven, a fairly large area, so that you can accommodate smaller as well as bigger length columns. Okay. And there are two types of column ovens actually available. One is called as forced air circulation, which is this type. Okay. And other one is called as heat block column oven. So heat block type of column oven, there will be heated block on which your column will reside, and those are generally aluminium block, and it will transfer heat to your column. There is one slight disadvantage is that the part which is coming directly in contact with heat block might get some extra heat as compared to other part. Okay, so heat blotches might get formed. To avoid this scenario, here forced air circulation type of column oven is used. Can you see? Okay. So here column is not coming in contact with any hot surface. Okay. This entire chamber will get heated up, and there is fan rotating behind, which will circulate this hot air uniformly throughout the chamber. So uniform heat distribution is there, and there will not be any heat blotches forming. Okay. So that is the advantage of column oven. Okay. This part is called as flow control valve, FCV. What is the use of this part? If you want to minimize the contamination of MS, you can use FCV. For example, I know that up to 10 minutes, all my peptide peaks are coming out of the column, and from 10 minutes to remaining 5 minutes or more 10 minutes, whatever is coming is a unwanted thing from the tissue lysate, which I don't want to send to mass spec because it might contaminate my mass spec. So I can give commands. Okay, here you can see the column outlet is coming to this particular valve. There is another valve which is going to the waste, and another valve which is going to the MS. Okay, so I can give command like from 1 to 10 minutes, pass the flow to MS, and once my all peptide peaks are eluted, direct the flow to waste. So it will not contaminate my mass spec. Okay. There is one small guard column also used here. Guard column is nothing but small cartridge which is filled with exactly same material as your column. Suppose you are using C18 column, guard column will also have C18 cartridge. Purpose of that is it will remove the unwanted matrix component, so that life of your column will be increased. Okay. Now we will move on to, okay, have you observed whatever columns we are using for this analysis, fast HPLC, are fast columns, okay, or UHPLC columns. So these are different from your conventional analytical column. So conventional analytical column will have 15 to 250 mm, 25 centimeter in length, 4.6 mm ID, and 5 micron particle size. But these columns are fairly short. Their IDs are also low, and micron size is particle size is 2.2 micron or 1.6 micron. So whenever you are performing the analysis on this kind of columns, the back pressure generated by these columns are very high. Okay. So here what will happen, if on conventional HPLC systems, if your runtimes are like 60 minutes or 70 minutes, on this column your runtimes will be 10 minutes or 15 minutes or lesser than that. Now if that means your peaks are eluting out very fast. From the column outlet, your mobile phase along with your analyte is passing through this capillary. Okay. Now this ESI is wireless ESI. So you will not see any voltage wire or nebulizing gas attachment. Nothing will be seen. This is just, you can remove the probe and directly put the probe. So you don't have to adjust or put in any wires or nothing. All these are made internal connections. Okay. So mobile phase will pass through this capillary, and surrounding that capillary there will be a flow of nitrogen gas, as well as this is a heated ESI probe, there will be again air, heated air passing through the surrounding the capillary. Okay, nebulizing gas is nitrogen and the heating gas is your zero air. So to this capillary we also apply high voltages, 3 to 5 kilovolts. Okay, so what will happen in this chamber? There is a liquid flow surrounding is the gas flow. So it will get sprayed in the form of droplets, right? And those droplets will have charge. Now, if you see here, in this chamber also we provide heat. Okay, so slowly you are using, in case of LCMS, generally volatile mobile phases like only water or methanol. Even if you are adding some buffers, those are volatile buffer. So whatever temperature you apply to this chamber ranges from 200 to 500 degrees centigrade. So everything will start evaporating. So droplet will shrink in size. So what will happen? Whatever charges are present on the droplet, they will start coming closer and closer. And those all charges are same charges, positive, 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 or negative, negative. So slowly repulsive forces will increase. And one point will come, which is called as welling limit, where repulsive forces exceeds the surface tension force and droplet cannot hold its size and it will burst into smaller droplet. So this process will continue till only your analyte containing the charge will remain. And this is how ionization takes place in case of ESI mode. Then if you see here, the spray position is like this, and your entry to the mass spec or triple quad mass analyzer is at 90 degrees. So all your unwanted mobile phase is going to the base, and only your analyte is taken to the mass spec. Of course, small amount of mobile phase will also enter, and to remove that there is a dissolution line. So dissolution line also we apply some sort of heat, and that will evaporate remaining traces of the mobile. And after ion guides, there will be first quadrupole, then there will be collision cell, which is nothing but your second quadrupole, and then there is a third quadrupole, and finally the detector. Detector is your electron multiplier. Okay, here one more thing, one special feature of this collision cell is it has UF sweeper that already has been explained, right? So like I explained you, carryover effect, same carryover effect can come in your mass spec as well, right? So suppose I am monitoring one particular transition. So that peptide went inside the collision cell, it generated some fragments, okay, and I detected the fragments. But if all the fragments are not getting emptied from that collision cell, then I started monitoring my second peptide. Some of the peptides fragments are common between these two transitions. Then I can get enhanced signal because of the traces of previous transition ka fragment. So that is called as crosstalk, right? And I want to avoid the crosstalk. So how can I avoid the crosstalk is I have to empty my fragments very fast from that collision cell. So here design of collision cell is unique. It is not like straight collision cell. It is slightly angled collision cell. Towards the end, it is slightly angled like this manner. Okay, and you apply pseudo potential. Okay, so your potential increases from this point to this point, and so ions will travel very fast in this manner and get emptied from the collision cell very fast, and that is why that is how you can reduce the crosstalk. And secondly, here see the concentration of argon gas present in your collision cell, that also you can control. So there is a variable levels of argon. So default is 270 kPa. But if you feel that okay, that is smaller amount of argon and this is not giving me good fragmentation efficiency, I can increase the amount of argon up to 450 kPa as well. Okay.